question, Jess, is it involves the historical context in which quantum mechanics was invented. It was a time when physicists were immersed in wave mechanics.
Mm-hmm.
They knew much more about waves than you guys do. And so this is really not far removed from the study of waves. It's just a little bit abstract. But then it gets worse as it goes. So anyway, I'm not really answering your question. Let's see, your partial t.
You kind of are.
Not really. Psi star psi. It's a cheat. Partial t of psi star psi is partial psi star partial t psi plus psi star partial psi partial t, right? Then, what I do is we can trade partial psi partial t for what? See up there? You know what we should do? Without loss of generality, we can multiply this by... I mean, if this is going to be 0, so is IH bar times it, right? It'd be so much nicer to multiply this by IH bar, wouldn't it? See, because then I've got... See why I did that? No, it's not quite what I want over here because I need the IH bar inside the conjugation. So to bring the IH bar inside the conjugation, that costs me a minus. Now there I'm assuming that the conjugate of the derivative of the wave function is the derivative of the conjugate wave function. In other words, that you can differentiate then conjugate or vice versa, and it's the same. You can prove this with advanced calculus. Let's not do it. It's not that exciting. So I did that there though. And then, so this, well, we go up there, right? So we got minus, you got yourself h bar squared over 2m. I'm going to write psi xx plus v psi, and then plus, oh, that's all times psi. And this is all conjugate of all that. Plus psi star, and again all this stuff, right? So the cool thing is, of course, that that's minus h bar squared over 2m psi x conjugate psi plus v psi conjugate psi, because we assume that the potential is real. Okay, the potential is real. I mean, it's a real potential. So h bar squared over 2m psi star psi xx plus v psi star psi. I was supposed to have a minus here, right? Huh. Alright, so some of these terms obviously cancel, right? But we are left with something. What's this equal to? So we got I h bar partial t of psi star psi equals to minus h bar squared over 2m, right? Or just say h bar squared over 2m. And there we got, I'm supposed to have a plus. This is supposed to be a minus, right? So that makes this first one a plus. So h bar squared over 2m psi star xx psi minus psi star psi xx. Now I do something sneaky here. I say that this is equal to like h bar squared over 2m of, I say, let's see here, partial psi star partial x psi minus psi star partial psi partial x. How on earth did I do that? Oh, and there's a partial x out here. Oh man, we're out of time. I'm in trouble. We're not in trouble yet, but we're working on it. Quiet. So if you do this differentiation, right, you get the second derivatives, like we have up here, and you also get partial x, partial x, partial x, partial x, but those cancel. So this is adding 0 in a sneaky way. These are literally equal. It's just an identity. Now that's pretty awesome because then you can look at partial t of the integral from minus infinity to infinity of psi star psi dx. We just calculated to pass that inside, right? Pass derivative inside. Pass the derivative inside the integral. Sure, what could go wrong with that? And that will give you, I guess I gotta say, h bar squared over 2m divided by IH bar, right? The integral from minus infinity to infinity, partial x of that stuff. You know. Right, and that of course is equal to h bar over 2mi partial psi star partial x psi minus psi star partial psi partial x evaluated at minus infinity. So, but since we are assuming that the integral, the square integrate, the integral of psi star psi is 1 from minus infinity to infinity, it implies that this and that are 0, right? So this is equal to 0. Consequently, we see that if we normalize, right, if we normalize the wave function at one time, it's going to stay normalized. And also this helps us to believe that the probability interpretation of the wave function is at least consistent, if nothing else, with Schrodinger's equation. Right? Now you can ask the question, why on God's green earth is there Schrodinger's equation and is there a wave function? And you're welcome to ask that. So next time, guys, what I'll do is I'll show you how we can calculate the, we'll look at like the expectation value of x, and I'll continue down this path, and hopefully we'll solve the quantum harmonic oscillator next time. So I think we'll have to spend 3-4 class meetings on quantum mechanics for it to start making sense. As soon as that happens, I'll stop working on it. Okay. Some people say quantum mechanics is not something you understand, it's something that you do. So we have to do it to understand it.
Interesting.
Maybe,
so it's abstract.
I don't know. If Richard Feynman said he didn't understand quantum mechanics, I don't think there's much hope for us.